So let me introduce Dr. Metcalfe. He works at Space Science Institute in Boulder.
Didn't know we had sound effects.
You never know, Travis. You never know what you get to hear. He works at Space Science Institute in Boulder, and he does all the cool stuff. And tonight his topic is about how to find planets around other stars. And that is a really intriguing technology. When I worked at Ball, we were working on the forerunner to that satellite, Kepler satellite. And it's amazing what they have done so far. There must be thousands of planetary possibilities out there that they have identified, right? That they still have to validate, but thousands. So are we alone in the universe? Not so sure. Will we ever know for sure? Not so sure either. But maybe Travis can answer those questions. With that, I'll give you Travis Metcalfe. Thank you.
Thank you so much. I'm really happy to be here and share with you the amazing progress we've made just in the last 5 years in particular on this question of are there planets around other stars, and are there other planets like ours? If you're like me and you've ever looked up on a clear dark night, you probably wondered whether there was somebody on another distant planet looking up at a clear dark night and wondering if there's somebody on the other end, you know? I think we all have those thoughts, and what I'd like to share with you tonight is the story of how a space telescope that was built just down in Boulder has pushed us closer to an answer of how likely it is for there to be life in the universe. I'll come back to that at the end. But in the meantime, I'm going to tell you a little bit of history about the search for planets around other stars over the last 25 years or so. And then tell you a bit about the Kepler mission, the space telescope that was built in Boulder, and how it changed our view from what we knew beforehand, just since 2009. And in the end, just come back to this question of what it means, what these new discoveries mean for the chances for life in the universe. But let's start close to home. So for most of history, we only knew about 5 other worlds in the solar system. Here they're shown to scale relative to each other, so the correct relative sizes, but of course the distances are much more spread out than this. So you probably recognize our home planet right there. And these planets, the word planet comes from the Greek word meaning wanderers, because they're bright lights in the nighttime sky that move relative to the background stars. And so the ancients knew these 5 other worlds as planets. But then the first change to the story came after the invention of the telescope. And in 1781, a British astronomer discovered the planet Uranus. And it took some time before Neptune was found. It was actually predicted to exist from its gravitational influence on the other planets by a French mathematician, and then confirmed and found right where it was predicted to be in 1846. Now I've left off Pluto. As you may know, about 10 years ago, Pluto was demoted and now is no longer considered a planet. There's actually a good reason for that. It's that technology was improving and we were able to find very distant worlds like Pluto in the outer solar system. And we started finding lots of them, hundreds of other planets or other bodies, icy bodies in the outer reaches of the solar system. And we didn't want to make school kids learn the names of all 100 of these planets. And so instead, we just redefined Pluto as a dwarf planet. It's no demotion, really. It's just a recategorization. So Pluto and lots of other things just like Pluto are in the outer reaches of the solar system, But for now, these 8 planets are all we have in our own solar system. The first planets to be discovered outside of our own solar system were not discovered until 1992. And they were kind of strange planets. So they were found around a thing called a pulsar. Now, a pulsar is a very tiny, compact star. It's about the size of New York City. But it's what's left over after a huge, massive star explodes at the end of its lifetime. And this tiny thing that's left over in the middle, from the middle of that star, is rapidly spinning, and it gives off, some of them give off radio waves in 2 sort of beams that sweep around as the star rotates very quickly. It rotates 1,000 times a second. And these radio beams, if we're in the right place, will sweep right across the Earth, and we can see them as little pulses of radio waves, not unlike what's going on in this television monitor behind me. Now, this particular pulsar, people noticed that normally the radio beams sweep by very regularly, once every thousandth of a second, once every millisecond. But this one, sometimes the pulses would arrive a little bit early, and sometimes a little bit late. And if you looked at how those pulses arrived over time, you could infer that there were planets orbiting around the pulsar, causing the pulsar to move around in space and delay the pulses from getting to us sometimes, and sometimes coming sooner than we expected them. And so just from timing the pulses from this strange pulsar, we were able to astronomers were able to determine that there were 3 tiny planets orbiting around this pulsar, all of them closer than Mercury is orbiting the sun in our own solar system, so very tightly close to the star. And tiny planets, 2 of them were only 4 times the mass of the Earth, and the smallest one was only 2 times the mass of the Moon. So really, really small compared to certainly what we were able to detect around other stars, regular stars, in 1992. Now, the thing that makes these planets not so satisfying is that because the pulsar was created by the explosion of a big star at the end of its life, probably these planets formed from the leftover debris from that explosion. They weren't planets that were there originally. They formed after the star died. And so they're not like the planets in our solar system at all. Nothing even close. But a few years later, the very first planet around a star like the Sun was discovered. And it was also not terribly like the planets in our solar system. This is actually a scale model of what that planet, that first planet, looks like. If this is its sun, and this is a planet about half the size of Jupiter, and that's the correct distance between them given the size of the stars there. Now I've got a little demonstration to help you understand how we found this first planet. Basically, we tend to think of planets as orbiting around their star, but in reality, the planet and the star orbit around a common center of gravity. So while the planet is orbiting the star is also wobbling a little bit around the center of gravity of the system. So I could tell you that, but it's easier if I show you that. So this is our little solar system, the star and the planet. And watch the star wobble as the planet orbits. Did you see it? Yeah. So certainly the planet is going around very fast around the star, but also at the same time, the star is wobbling. And we can measure the wobble of a star because if you pass the light of the star through a prism and spread it out into the rainbow of colors, you can see these dark lines that are caused by the chemical elements that are in the atmosphere of the star. And those dark lines, because of the Doppler shift back and forth as the star moves towards and away from us due to this wobble of the planet. So that's how the first planetary system around a star like the sun was discovered. Just this, call it the wobble method. But not until 1995. Again, a planetary system very unlike anything in our solar system because, here we have a planet almost the size of Jupiter, but orbiting closer than the planet Mercury does in our own solar system. So very, very close to its star. And the reason for that is that's the easy kind of planet to detect because the closer it is to its star, the more it's going to make the star wobble. Okay. In 2001, the next landmark was that the first time we saw a planet actually pass in front of the face of a star while we were watching. So it's a little bit like an eclipse, but like a solar eclipse, but instead of something covering the whole face of the star, it just covers up a little bit of the star. Now, planets are oriented pretty much randomly in space, and so you just have to be lucky that the planet is, if you look at enough stars, then one of them that has planets is going to be oriented just right so that planet passes across the face of the star as you're watching. So if you look at enough stars for long enough, you can see one of these shadows of a planet sweep across your view as it blocks out maybe, so something the size of Jupiter blocks out about 1% of the starlight for 10 hours, once every orbit. And so that was the first time this was actually seen in 2001 was from a telescope that was built at NCAR down in Boulder. And they put the experiment out in the back parking lot and just had it monitor all these stars. And there they discovered the first transiting planet. And again, because of the detection method, you're biased towards big planets in close orbits because then they go around more often and your chances of seeing this shadow pass you are greater. So again, it's a very unlike anything in our solar system. Big Jupiter-sized planet in a close orbit like Mercury. I'll just tell you about some of the other methods that have been used successfully to detect planets, even though relatively few planets have been detected by these methods now, because there's some strange ways that you can use to find planets around other stars. In 2004, the first planet was discovered by a technique called microlensing. Now, Einstein's theory of relativity told us that gravity can sometimes act as a lens, and if you have a nearby star that passes directly in front of a more distant star, it will magnify the light of that star as if it's closer, just while it's passing in front of it. So you have to be lucky. You have to be looking at a large number of stars and just happen to see two pass in front of each other. And if that star in the foreground has a planet, then that planet will also magnify the light for a short period of time as it passes in front of the background star. And so in addition to this magnification of the light that you get from the star, you get a little blip from the planet. That's an additional bit of magnification. And so in 2004, this technique was used to discover the first planet. And it was a little bit more like the planets in our solar system, a Jupiter-sized planet, but in a wider orbit, more like out at the distance of Mars. So not so different from our solar system. But again, it was not a sun-like star. It was actually a tiny red dwarf star, which is maybe less than half the size of the sun and much, much fainter. So. In 2008, we got the first direct image of a planet. This is what everybody had been waiting for, the real proof that it actually is a planet, right? That you can actually see it with your eyes. You're not just using these fancy methods to detect it indirectly. This is a picture from the Hubble Space Telescope where they blocked out the light from the central star, so that's the shadow that you see here. And a lot of this is scattered light, but you see a dust ring here. And what they noticed was a little dot just on the inside of that dust ring. And here's a magnified view. And what they suspected was that that little dot, it didn't correspond to any background star. And so they came back a couple of years later to see if that had moved around in an orbit. And sure enough, it had. And so while this was a background star that stayed fixed relative to all that other stuff, this one moved around in an orbit, so it, revealing that it was an actual planet. Now this is a huge planet, 3 times the mass of Jupiter, in a very wide orbit, because it has to be able to directly image it around even the nearest stars. So its orbit is 3 times the size of Neptune, which defines the outer part of our solar system. And the host star in the middle there is about twice the mass of the sun. So still, even by 2008, most of the planets that we'd found around other stars were very unlike anything in our own solar system. I should just mention that after the 2008 discovery, we repeated this and detected a direct image of a planet around another star from ground-based telescopes as well. You don't need the Hubble Space Telescope. You can actually do this from the biggest telescopes on the ground as well. Okay, so by 2009, hundreds of planets around other stars were known, but most of them were these strange so-called hot Jupiters, big planets very, very close to their stars, not at all like the stuff in our solar system. But what we really want to find are planets more like the Earth. And if you want the planet to be able to host life, then it should be small and rocky, so it should be less than a couple times the size of the Earth. And it should orbit at a distance from its star where the temperature is just right for liquid water to exist. We think water is an essential ingredient for all life. So that basically, if you're too close, then the water is going to boil away like Venus. And if you're too far away, then it's going to freeze out like Mars. And so that just defines this sort of green zone, which we call the habitable zone, or the Goldilocks zone, because it's just right temperature. So, leading up to 2009, down in Boulder at Ball Aerospace, they started building this space telescope called Kepler, after the ancient astronomer. And Kepler, you know, it's not the biggest space telescope out there. The Hubble Space Telescope is the size of a school bus. And poor little Kepler here is more like the size of a Prius. But it got the job done. Again, the mirror is not the biggest mirror. It's less than half the size of the Hubble Space Telescope. But with a mirror this size, you can see stars that are 10,000 times fainter than you can see with your naked eye. So very powerful. And at the focus of this big mirror, they have this huge digital camera that covers 100 square degrees of the sky and just snaps images every 30 minutes to monitor the brightness of lots and lots of stars. So in 2009, Kepler was launched from Cape Canaveral, Florida. It was a night launch. This picture was taken just shortly after it had shed its solid rocket boosters. So I was there for the launch, and when I saw these little things falling off, I thought, oh no, it's exploded. But it got up okay, and basically Kepler just follows the Earth in its orbit around the sun. So it's close enough that you can keep in regular radio communication to download the images and all of that, but far enough away that it's not disturbed by the glare of the Earth and the Moon. And so from 2009 to 2013, the 4-year mission, Kepler just stared at this 100 square degree patch of the summer Milky Way. So this is 400 times the size of the full moon in the sky. You can see here the summer triangle. So it's close to the plane of the Milky Way, so there's lots and lots of stars there, but it's a little bit out of the plane so that the stars aren't too crowded together. You can still measure their brightness separately and reliably. And so just for 4 years, it would just take images and measure the brightness of 150,000 stars in that field of view. Now, some of those stars are going to have planets, and some of those planets will be oriented just right. A few percent of them will be oriented just right so the planet will pass in front of the star. So this transit method, seeing the shadows of planets pass in front of our eyes. That's what it was looking for. Now, from the edge of our own solar system, the Earth will block out 0.1% of the sun's light once a year for about 10 hours. And then a year later, 10 hours, it'll block out another 0.1%, and it'll happen again a year later. And that's what Kepler was looking for, the signature of these tiny planets like the Earth, just measuring very, very precisely the brightnesses of all these stars, hoping that a few percent would show these tiny dips in brightness, regularly spaced a year apart or so, to reveal the presence of these Earth-sized planets. So before Kepler, from the other ways that we detected planets around other stars, we could only really detect these big ones, right? And so we knew that just maybe a few percent of stars had planets the size of Jupiter or Neptune. But we didn't know how common the smaller planets were because we couldn't detect them. There was just no way with the other methods that we could detect them. But after Kepler's 4-year survey, what we found was that tiny planets like the Earth are actually the rule, not the exception. In fact, most stars in the sky probably have at least one planet smaller than Neptune. That's a big deal. That's a big change in our view of how common planets are around other stars. So let me briefly look.
Travis, are
yeah.
they mostly gaseous planets, we think, or are they also rocky planets?
So the transition between rocky planets and gaseous planets is somewhere in here, somewhere around 1.5 times the size of the Earth. If you're much bigger than that, the gravity is strong enough to hold on to those gases, and then you get bigger just from being more like Neptune or Uranus. But we think anything smaller than about 1.5 times the size of the Earth is going to be rocky. Yeah. So all these planets on this side. Okay, so that's a huge transformation. And now that we know that tiny planets are the rule rather than the exception, what we'd like to do is find the nearest examples of them around the brightest stars in the sky. Because one of the limitations of Kepler is that it just stared at this one patch of the summer Milky Way, but those stars are actually on average hundreds or thousands of light years away, really far away, not next door in the galaxy. But because the planets are so common, these small planets, we know that it's now worthwhile to survey the whole sky and try to find the nearest examples where we could actually hope to directly image those planets and maybe even get information about their atmospheres and their composition, which we couldn't do for the more distant planets just because they're too faint. And so the successor to the Kepler mission is already approved for launch next year. It's called the Transiting Exoplanet Survey Satellite, or TESS. And that's exactly what it will do. It will try to find, using the same method that Kepler used for this one small patch of the summer Milky Way, it will survey the whole sky using that same method and try to find the nearest planetary systems like ours. So TESS is actually quite a bit smaller mission than Kepler. This is a full-scale model of the TESS spacecraft with the main science team at MIT in Massachusetts. And inside the barrel of that telescope of the satellite are actually 4 of these telescopes, or really large cameras. So this is one of the 4. The camera here, not this guy. I'm sure he'd like to go on for the ride, but. And so these cameras are arranged in the satellite in such a way that they're looking at a sort of strip of sky from the plane of our solar system, where all the planets are lined up in the same plane, up to the straight above the solar system. And it'll just do one strip at a time, each strip for one orbit of the moon, basically, for 27 days. So it's not going to stare for 4 years at any one patch the way Kepler did, so that's the part of the weakness, I guess. But it'll do each strip for 27 days. It'll take 13 strips in the northern hemisphere, and then it'll flip over and do the southern hemisphere. Now, this top camera is actually at the pole straight up, and so every time it rotates once a month, that field actually stays basically the same. And so for a full year, you'll have information from that camera. So you'll be able to get out to the orbital periods of things that are like the Earth around stars like the sun. And the same in the southern hemisphere as well. Okay, let me take a little detour just to tell you what my role has been in all of this. So I've been part of a team that uses a trick to try to characterize the planets around the stars that were observed by the Kepler mission. And the trick is that when you see a planet pass in front of a star and causing this dip in the starlight, what it really tells you is not exactly the size of the planet, it's the size of the planet relative to the size of the star. Because it's blocking out a fraction of the area of the star, and so it's only a relative measurement. You only know the properties of the planet as well as you know the properties of the star. And so our team was basically to try to characterize the star at the center of that planetary system so that we could learn the absolute size of the planet. Is it exactly the size of the Earth, or twice the size of the Earth, or half the size of the Earth? That matters, whether it's rocky or gaseous, for example. But also, we use this trick to measure the age of the star. And if you know the age of the star, since the star and the planets all formed at the same time out of the same gas cloud, if you know the age of the star, you know the age of the planets. So that would allow us to take these planetary systems and put them into a chronology, put them in order, into a sequence, and we could understand which ones formed earliest and which ones formed later. And the nature of that trick comes from the fact, so this is a close-up picture of the sun. This is a sunspot, just a magnetic spot on the sun that's a little bit cooler than the surroundings. This whole area is maybe 1% of the surface of the sun. We're really zoomed in here, but for scale, this is the size of the Earth. So, a typical sunspot is about the size of the Earth, which is kind of cool. But the thing to notice here are all these, you see these little bubbles? They're sort of bubbles. Those are, that's the surface of the sun boiling, basically. It's just boiling to try to get heat out from the interior. And those boiling motions, those things that are like the size of Texas, are turning over on the sun every 5 minutes or so. And that creates little, very, very low frequency sound waves that travel into the star and come back to the surface and cause brightness variations. Tiny brightness variations that we can measure. It's like seismology on the Earth. There's waves traveling through the star, and you learn about the inside of the star by studying those waves. And we study those waves just by measuring the brightness variations caused on the surface of the star over time. And that allows us to measure, very simply, the size of the star and the age of the star so that we can characterize the planets that are around it. So let me tell you about 2 specific discoveries that I was involved in that I'm most proud of, I'd say. Kepler 37 was discovered a couple of years ago, and it contains a 3-planet system, one of which is the smallest planet known outside of our solar system. It's actually smaller than any of the planets in our solar system, unless you count Pluto. The biggest of the planets is about twice the size of the Earth. The middle one is between Earth and Mars, and then the smallest one is smaller than the planet Mercury, almost as small as the Earth's moon. So that's about 30% of the size of the Earth. It's a tiny, tiny planet. And so you can imagine that if the Earth covers up, 0.1% of the starlight, that this planet covered even less. But these planets are all very close to their star, so they're not in the Goldilocks zone, the habitable zone where life could exist. But nevertheless, it is the smallest planet that we know of currently.
And the star, Travis, is the star about the same size as our sun, or is it much bigger?
No, the star in this system is actually just a little bit smaller than the sun. It's maybe 80 or 90% the size of the sun. And by measuring the size of it with seismology, with this trick, we were able to pin down the sizes, the actual physical sizes of these planets precisely.
Similar age as well, a couple billion years?
Yeah, a few billion years, yeah, not so different from the sun in this case, yeah. But this planetary system is the oldest that we know about. And in an interesting way, so Kepler 444, this was just discovered about a year ago. And it's a 5-planet system. All 5 of those planets are smaller than the Earth. Again, they're very close to their star, and so they're too hot to host life. But the interesting thing about this system is that from seismology of the star, we determined that the system is 11 billion years old. Now, the universe itself is only 13.5 billion years old, and so that's almost as old as the universe, certainly close to the age of the galaxy. And so what it suggests, which was a surprise, is that somehow stars are able to make tiny rocky planets like this, and have been able to make those tiny rocky planets since almost the beginning of the galaxy. And so even though these planets are not habitable, are not suitable for life, there are other planets out there that may be as old as this, twice or more than twice the age of our own solar system, that have rocky planets that are in the right place. It suggests that rocky planets have been forming since nearly the beginning, and that really boosts the odds for life in our galaxy.
Travis, this star must be fairly cool then if it lives that long, right? 12 billion years or 10 billion years?
Yeah,
It's a cool star.
it's a bit cooler than the sun. It's another one of these about 80 or 90% the size of the sun. The lifetimes of those stars are quite a bit longer. The sun will only last for about 10 billion years. So this is the smaller stars are a bit like cars. The small ones get better gas mileage, right? And so they don't burn through their fuel as fast, and they can live longer lives. That's basically how it works. Okay, so bring you up to date. By today, there are about a dozen planets that are almost as small as the Earth around stars of various types. So this is a star like our sun, and then smaller, cooler stars. There's a dozen stars that are almost as small as the Earth and orbit in that habitable zone of their star where liquid water could exist. These were all discovered by the Kepler spacecraft. And one of them is almost a twin of the Earth. It's a cousin. It's a little bit bigger, but it's far enough away from its star that it's like an Earth-like orbit. And it's small enough to be rocky. So now, of course, those dozen stars are just from the 150,000 stars that Kepler surveyed, right? And only a few percent of those stars have planetary systems that are oriented in the right way to be able to see the transit in the first place. Our galaxy contains a few 100 billion stars. And there are, at least 100 billion galaxies in the universe. So habitable rocky planets like the Earth are everywhere. They've got to be everywhere. And the Search for Extraterrestrial Intelligence, the SETI program, has already started listening for radio signals from these 12 planets that we discovered relatively nearby. No word yet. We haven't decoded their TV stations or anything. But my opinion is that it's not a question of if we will find other life in the galaxy. It's a question of when. So, thanks.
Are most of these stars in our local Orion arm in our galaxy? I mean, are in the local area around our solar system?
Relatively few of them are. We're looking towards closer towards the center of the galaxy, sort of at a neighboring arm. Most of the stars are sort of in the neighboring arm of the Milky Way galaxy. Yeah. Yep.
So the habitable planets, you're mostly just looking at whether they're habitable for humans or not.
That's right. So if our understanding of what it takes to support life is too narrow, then, we could have some latitude on that. So this is just an assessment of what kind of planets would be required, for humans or animals like are on the Earth. We know that life is pretty resilient. Even on Earth, if you go to the coldest places on Earth in Antarctica, or you go to the hottest places in the volcanic vents on the bottom of the ocean, there's life there. And so there's a whole range of temperatures where at least primitive life can get a foothold. And so, there may be possibilities for life in places that are even more extreme than these dozen good systems discovered by Kepler. Yeah. Yeah.
The Goldilocks Zone, that's liquid water on the surface, is that the parameter, the unique parameter?
Basically, it's a little bit hard to know exactly. We don't know exactly if there is liquid water there. All we know is how hot the star is at the center, and how the temperature would change if you're a certain distance away, right? But that's only a first approximation. Of course, if the planet has an atmosphere or does not have an atmosphere, and what that atmosphere is made of, that could make a big difference, right? So you can imagine a planet in our own solar system even, as far away as Mars, but with a thick atmosphere that trapped some of the heat. It could also be habitable. And there's talk of transforming Mars's atmosphere so that it could be livable for humans, right? So it's just a first guess. All these things are as narrow as possible, and there's latitude for sure. Other questions?
Well, I got one more. Well, now I read somewhere that they're starting to try to determine the atmospheric composition of some of these planets. So how would that be? Is Tess going to do that? Or?
Tess is going to find those planets. So the successor to the Kepler telescope, Tess, will find those nearby planets where other telescopes, and the successor to the Hubble Space Telescope is called the James Webb Space Telescope, or JWST. It's going to be launched around the same time as Tess, maybe a year later. And it will have instruments that will make it possible to measure the atmospheres of those planets once Tess discovers them. Okay, so we have to find those nearby systems first. And basically how that works is you're seeing a shadow go across the face of the star. But if there's an atmosphere, then some of the starlight is going through that atmosphere on its way to you. And if you spread the light out into the colors and look for the chemical fingerprints of that atmosphere, you might be able to do it. And it's actually been done for big planets like Jupiter around regular stars like the sun. And when they've detected sodium, carbon monoxide, several different elements. But the hope is to get down to these smaller planets like the Earth with regular atmospheres, not like the big gaseous planets, and see, for example, methane or liquid water, or not liquid water, it would have to be gaseous to be able to see it in the atmosphere, sorry. Or in reflected light, you might be able to see the signature of green plants on the surface. So there are several proposals for what would constitute a biosignature, a signature of life on the surface of a planet. And so that's maybe 10 years off. That's the next step. I personally want to intercept their radio communications. I think it would be a lot more fun. Listen to their radio, see if their politicians' speeches are any more entertaining. Yeah.
Is Kepler still taking pictures, or is its mission over?
Its main mission is over, but so you may have heard in 2013, just at the end of its 4-year mission, it lost the ability to point very accurately. And so it could no longer point at this one place in the Milky Way that it had been staring for the 4 years. But the clever engineers at Ball figured out a way to continue to point it only in the plane of the solar system. So you could look, so you roll it on its side basically and use the pressure from sunlight as the third wheel, basically, to stabilize it from rolling. And for 80 or 90 days at a time, you can look at different fields around the ecliptic plane where all the zodiac constellations are. And so it's been doing that for the last couple of years. And we just had a scare this last week where Kepler went into emergency mode, but they recovered it again. These things happen. It's 75 million miles away now, so it's a little hard to communicate with it. It takes 15 minutes to talk to it and get a reply. But again, it's still looking at new areas of the sky and finding new planets, continuing to find new planets, yeah, all over the sky. Yeah. Yeah.
So how much does our sun wobble considering all the planets are affected?
So it's mostly a result of Jupiter, although the other planets have some contribution. And the sun moves around the center of gravity of the solar system by about its own diameter. So the center of gravity of the solar system is near the surface of the sun, and it kind of wobbles around by its own size. Pretty close. I've never noticed it wobbling myself, but